Okay, so now we have glycogen synthesis. This isn't really going to be happening in the fasting state, but I'll talk about it briefly, and then we'll talk about why we want to inhibit it when we're fasting. So glycogen synthesis, again, comes from glucose. Glucose becomes glucose 6-phosphate, as we saw in glycolysis. It can also go to the pentose phosphate pathway and do some other things. Glucose 6-phosphate. So let's say we've got plenty of glycolysis, TCA, ETC happening. We don't need any more glucose 6-phosphate that way. It's going to back up. We don't need any more glucose 6-phosphate in the pentose phosphate pathway. It's going to back up. Now what do we do with the excess glucose 6-phosphate? We make some glycogen, store it for later. So glucose 6-phosphate becomes glucose 1-phosphate. So this is the activating step here. We need some UTP to provide some energy. So we get UDP glucose, which then is enzymatically processed to become glycogen. Now we have the glycogen that's already started, and we have glycogen synthase or the 4,6 transferase, depending on where we are in the chain of glycogen, that's going to take this and use it to build more glycogen. Now, again, this isn't going to be happening in the fasting state. If it were happening, we're talking about it is signaled by insulin, because glycogen synthase, this enzyme gets dephosphorylated, and therefore it gets activated and continues to build the glycogen. And that is triggered by insulin. And also it is stimulated by excess glucose in the muscle cells, because as we saw, if we have enough glucose, we don't need to do glycolysis. We don't need it in the pentose phosphate pathway. It's going to build up as this, and therefore we're going to want to store it. So we're going to send it through and make glycogen. So excess glucose is another thing that stimulates this process. We need UTP to help this part along and to keep this going. Now, in the fasting state, we don't want this to happen, so we want to inhibit it. So it is inhibited by glucagon, which inactivates glycogen synthase by phosphorylation in the liver cells. Now, in the muscle cells, glycogen itself is its own feedback inhibitor. So if we have enough glycogen, it's going to inhibit this process and say, hey, we don't need any more. And this is happening all the time in muscle cells because they are using energy so quickly. And also low AMP. So AMP is an indicator of low energy. So if that itself is low, we're going to inhibit this whole process, because it's, hey, we don't need to be storing energy right now. We need to be using it. So that is also an inhibitor of glycogen synthesis in the fasting state. Okay, now we're talking about glycogen degradation, which is happening in the fasting state. Definitely. So we have our glycogen, which is our stored glucose. We have the debrancher enzyme. We get a little bit of free glucose here that leaves. We also have some inorganic phosphate, helps this enzyme here to make the glucose 1-phosphate, which then turns into the glucose 6-phosphate, which we have seen over and over, which then can be used in glycolysis, the pentose phosphate pathway, or other things. Now, in the liver, glucose 6-phosphate is going to be made into free glucose, which will then go into the blood to supply the other cells. Now, in muscle cells, we're just staying at the glucose 6-phosphate and then using it for all these other things. But in the liver, we want to get the glucose out into the blood, so it's going to convert it to the free glucose, which can leave the cell into the bloodstream for the body to use. So now, glycogen degradation, we want this to happen in the fasting state, and it is stimulated by glucagon that will phosphorylate this enzyme, glycogen phosphorylase, in the liver cells. So glucagon is what is going to start this whole process, breaking down the glycogen with the glycogen phosphorylase. Epinephrine or other stress will also stimulate this to happen in the liver cells, saying, hey, fight or flight, let's go, let's mobilize some of this energy. So that can also happen, not necessarily just in the fasting state, but in a state of stress, fight or flight. Now, low energy inside the muscle cells will also stimulate this to happen, because we saw in glycogen synthesis, low energy inhibits that. So low energy is also going to activate this process. And also calcium in the muscle cells plays a role in activating this process, because it's saying, again, hey, we're working hard here. Let's go. Let's get this going. Let's mobilize some of the stored glucose and get it to where we can use it. Now, glycogen degradation is inhibited by insulin, because that dephosphorylates this enzyme, which makes it inactive, and it stops this from happening. So we're not breaking down the glycogen, and we're free to start rebuilding it if we need to. And that's what happens in the fasting state, glycogen degradation. Okay, gluconeogenesis in the fasting state. So this is important in the fasting state because we are making glucose. So we've used up our dietary glucose. We've probably used up our glycogen. So we want to make glucose out of non-carbohydrate substrates. So where do we start here? Let's start with acetyl-CoA, right? Acetyl-CoA and pyruvate. So these things can come into the mitochondria. So, this is a lot. Fatty acids, from the fatty acid breakdown, which is happening in the fasting state, we get acetyl-CoA. Acetyl-CoA then activates this step. So we've got some pyruvate, which can come from lactate, pyruvate into the mitochondria. Pyruvate carboxylase will convert this to oxaloacetate. Oxaloacetate cannot leave the mitochondria. It becomes aspartate and malate. They leave and re-become oxaloacetate. Now that's important, because you don't always want this to happen, because if you need energy production in the TCA cycle, you're going to want to keep this in the mitochondria. You don't want this to leave all the time. So that's important. So it can't leave. It becomes these two in order to leave. Now, oxaloacetate, this is a key step. Phosphoenolpyruvate carboxykinase. I think I said that right. This step here converts oxaloacetate to phosphoenolpyruvate, which then essentially goes in reverse glycolysis until we get the glucose, which is what we want in gluconeogenesis. So we have some others. This is essentially the same, except a couple things are different here than if glycolysis were going this way. So we have this fructose 1,6-bisphosphatase is an important step that is different than if you were to just do reverse glycolysis, because you can't, because those are irreversible reactions. So if we're going to make glucose, we need different enzymes to make those irreversible reactions happen. So we have fructose 1,6-bisphosphatase. We also have glucose 6-phosphatase in the liver again, because that is going to be what's making the glucose, the free glucose that can go into the blood and be distributed. So let's see, we can also get some glyceraldehyde 3P and DHP from glycerol, which is also a product of fatty acid oxidation, which is happening in the fasting state. So we've got fatty acids, pyruvate, acetyl-CoA, glycerol, all going into this, making this happen, all mostly results of fatty acid oxidation, which is a signal that we are in the fasting state. We've got no dietary glucose. We probably used up our glycogen, so we're going to need to start going after some fatty acids to make some glucose. And also some other things, you can use ketones. I'm sorry, that's not correct. Start over. So we're going to need to use fatty acids to start to make glucose. And also pyruvate can come into this. Now, pyruvate can come from here. So say we've gone through glycolysis and we've made a lot of pyruvate, but oh no, we ran out of glucose. Now pyruvate can go into this and rebuild some more glucose that can be used in the cells. So this whole process is stimulated by acetyl-CoA, which activates pyruvate carboxylase, which needs biotin and magnesium to convert pyruvate to oxaloacetate. Also needs ATP and some carbon dioxide. Phosphoenolpyruvate carboxykinase down here is induced by glucagon, also stimulated by epinephrine and glucocorticoids and AMP. So low energy, low blood sugar is going to stimulate this pathway to happen. Because remember, if we don't need to be making glucose, chances are we're burning glucose using it. So we don't want this oxaloacetate to be converted. We want that to stay in the mitochondria and be used in the TCA cycle. We don't want to use it to make more glucose if we've already got glucose. Pyruvate kinase, this enzyme right here, is inactivated by glucagon. So that is the one that would send pyruvate into the TCA cycle. And if we don't have any glucose, we don't want the pathway to be going this way into the TCA cycle. So glucagon is going to inactivate pyruvate kinase, which is going to cause a buildup of phosphoenolpyruvate, which is then going to move in this direction. Also, we have NADH from fatty acid oxidation, blocks this pyruvate dehydrogenase complex. So NADH, we're breaking down our fatty acids. So we get some acetyl-CoA, we also get some glycerol. Now the acetyl-CoA is going to go to work on this enzyme, but the pyruvate can turn into acetyl-CoA. We don't want that to happen. So the NADH from fatty acid oxidation as well blocks pyruvate dehydrogenase complex. So we get a buildup of pyruvate. It can't go this way. It's going to go this way and then result in this ultimately. Now G6P and F16B are induced during fasting. So these two enzymes, which are the special enzymes that take the place of the irreversible steps in glycolysis so that we can do this backwards, they are induced in the fasting state. They're upregulated, I believe it's genetically, to be more available for this to happen. Now, in the fasting state, we want gluconeogenesis. We want to be making glucose so we can use it for energy. But what are the things that are going to inhibit it? We have phosphoenolpyruvate carboxykinase is inhibited by insulin. So say we've made some glucose and then we eat, the insulin is going to come in and inhibit this from happening. Therefore, this oxaloacetate won't transfer over here and it won't go back this way. Oxaloacetate will tend to go back into here. We've got insulin, meaning we've got glucose. So the glucose is going to come in into the TCA cycle, and we can use this oxaloacetate and the acetyl-CoA in the TCA cycle, meaning we don't need to do this anymore because we've got glucose. Thank you, insulin. So now we're going to talk about the pentose phosphate pathway. We have phase 1 and phase 2. Now phase 1, we have irreversible reactions. They're also oxidative reactions. Phase 2, they are all reversible reactions and they are non-oxidative. So here we go. Pentose phosphate pathway. We have excess glucose 6-phosphate in the cell. We don't need it to go through glycolysis. It's excess, so it's going to decide to go through this direction. Glucose 6-phosphate, G6P dehydrogenase, stimulated by insulin. So if we've got high glucose in the cell, chances are we've got high glucose in the blood. We've got insulin, so it's going to activate this enzyme. Also needs water and NADP, and this creates NADPH. Now NADPH is also created back here. That goes into an antioxidant activity to be recycled and restore other antioxidants. It also can be used for fatty acid synthesis, which makes sense. If you've got a lot of glucose, you're going to want to build fatty acids. Same thing with cholesterol synthesis. So NADPH, important result of these steps here in phase 1. So glucose 6P dehydrogenase converts the excess glucose 6P into 6-phosphogluconolactone. That then becomes this 6-phosphogluconate, and then insulin again will activate the 6-phosphogluconate dehydrogenase to make ribulose 5-phosphate. And again, we have the result NADPH, which can go and do these other important jobs. Now, this is all in the presence of excess glucose and therefore insulin. Now, this happens, we need 2 of these to enter phase 2, ribulose 5-phosphate in phase 2. Now, we're going to shift some carbons around. We get a ribose and a xylulose. The ribose can then be used for DNA synthesis or not. It can also do this. Now, xylulose will become these, and we're shifting carbons around. We got transketolase, transaldolase. We need thiamine pyrophosphate to make this happen. We've also got a transketolase that can take the erythrose into the fructose. So we've got excess glucose. We're going to go through all this. We're going to get the ribulose. We're going to maybe make some DNA. And we're going to shuffle some carbons around. Now we're going to get some more intermediates of glycolysis. So if we've used up our sugar at this point, right here, these can go back into glycolysis and make some more energy. So another thing to know about this is phase 1 is not dependent. I'm sorry, phase 2 is not dependent on phase 1. So if we need some ribose, 5P for DNA synthesis, but we don't have all this happening, that's okay. We can get some substrate from fructose 6-phosphate glyceraldehyde 3-phosphate, and we can shuffle them around and make some ribose 5P anyway. We don't need this to happen. Now, this pathway is stimulated by excess glucose in the cell. Don't need it for glycolysis, so it's going to come over this way. And insulin, if we've got excess glucose, we've got insulin. It induces glucose 6-phosphate dehydrogenase synthesis. So it's going to actually make more of these enzymes to make this happen more. And it also activates 6-phosphoglucanate dehydrogenase. So it makes more of these, and it also activates these. That's going to help this whole process along. So insulin. Also, glycolysis intermediates, G3P and F6P, down here. If we've got a lot of those built up from glycolysis and they're not continuing down because of the rate-limiting steps in glycolysis, they can come in here and make some nucleotides. Also, another thing that will stimulate this is if we have more NADP than NADPH, we're going to want some NADPH, so we're going to use up the excess NADP, and we're going to make this happen and happen here to get some more NADPH. So that is going to also stimulate this pathway. We need magnesium and calcium as well as thiamine pyrophosphate for phase 2. Now, inhibited by, if we have excess NADPH, that will inhibit glucose 6-phosphate dehydrogenase until it is used elsewhere. So if this builds up and it's not being used as an antioxidant, fatty acid synthesis, or cholesterol synthesis, it's going to build up and it's going to block this enzyme saying, okay, glucose, go and do other things now. Also, glucagon is going to block this enzyme. I'm sorry, the glucagon actually down-regulates this enzyme so that more glucose 6-phosphate is available for other things. And also high glucagon, oh, that's what I said, okay. So in the pentose phosphate pathway, it can happen during the fasting state. More likely it's going to happen in the fed state because here we've got excess glucose. But if for some reason we've got a buildup of fructose 6-phosphate glyceraldehyde 3-phosphate, we can make some nucleotides even in the fasting state. So we don't need to be in the fed state for this to happen, but most likely it would happen more in the fed state than not.